Good morning, I am Suryakanta Biswal. So today's my topic is optimal sensor placement strategy for the identification of local bolted connection failure in steel structures. So my content is, first I will introduce why we need the optimal sensor placement strategy, and I will discuss few of the existing strategies also. Then I will define my objective for this study, followed by development of the new algorithm, then one of the case study, then results, then conclusion. So we are working on one of the project where the aim is to identify the loosening of a few of the bolts, not all of the bolts at the two ends of the steel beam. So this is a steel frame. So in the steel frame there are 4 bolts here, 4 bolts here. So if you loosen one or two of them, could you identify using vibration signature? So that was the aim of the study here. So okay, so we can do that, but what to measure, where to measure? So those are the two questions that are raised. So another another project we are also working on for network rail. So there is a steel girder here. It's not taking the track load. So it is on the side, it's taking the load of the cables, the electrical cables. But the ends, both the ends of the girder, they are put brick masonry. So it is embedded inside brick masonry. So due to weathering, it cracks and water goes into the brick masonry, so it corrodes. So if you see, the ends become less. So there are big holes at the ends. So to monitor them, they need to break the end blocks. So if there is a damage or there is no damage, they have to break it to check it. So they wanted to avoid that. So they said, could you identify the holes, something like this, without breaking the end blocks? So if you consider a typical health monitoring problem is to estimate the probability density of the target theta. Theta can be anything. It can be damage indicator, it can be random variable, the random parameter of the FE model, it can be anything, given the measurement Z. So to estimate the damage, we need the measurement. And the measurement, the questionnaire is how many sensor, what type of sensor, and the optimal location of sensor. So most often this part is ignored. So they use whatever sensor they have in their lab and how many sensors they have in their lab, but they forget about the optimal location. So today my topic is to find the optimal location of the sensors. So a few of the existing techniques to identify the optimal location of sensor is based on to find the modal information matrix or the mode shape matrix. So based on the matrix, there are few of the algorithms already present, but they tell you if your concern is to identify the modal matrix, you can follow any of the algorithm. Apart from this algorithm, which states to identify the damage also based on the modal properties. Okay, so but the issue with this technique is you can identify the damage when the damage is located at any one of the sensor locations. Okay, so if the damage is at the ends, you cannot identify using this method. The damage should be at any location of the sensor or along the length of the member, not at the ends. So the other technique is, okay, you can identify the modal properties like frequencies or mode shapes using any 4 of these algorithms and use them to identify the damage. Okay, so let's try that. So for the steel frame, we consider different damage scenarios. Here we have considered 10 damage scenario with a different combination of bolts loosened. So either 1 loosened, 2 loosened, or 1 or 2, 3, or finally 1, 2, 3, 4. All the 4 bolts at one end. So using the frequency data, so we extract the frequencies. And if you see the change in frequency, you can only capture around 4 to 5% change for the damage case 10 when all the 4 bolts have been loosened. Okay, so but all other 9 cases, the change in frequency is less than 2 or for maybe for the 9th case it is around 3%, but for all 8 cases it is less than 2%. Okay, so when the change is less than 2%, it is very difficult to identify the damage using the modal properties. If you see the mode shapes also, you can see only the 10th damage case, you can actually visualize the change in mode shape. In all other 9 cases, it's identical, they are identical. So using modal properties, it's very difficult to identify the damage. So the next question is, how about time series data? So using time series data, could you identify the damage? Okay, yeah. So yesterday Dr. Ing presented about using time series data to identify damage. Like he could identify few of these 9 damage cases using deep learning and using time series data. Okay, so there is hope. So there is promise that we can use time series data to identify few of the damage cases here that we could not identify using modal data only. So here our objective is to find the optimal location of sensor, at which if you take the measurement, the change in measurement means the change in time signal before the damage and after the damage will be maximum. So we need to maximize the change between the time signal before the damage and after the damage. So that's our objective. So based on this objective, we will find the optimal location of the sensor. So now to find the change in the time signal, one good measure is to find the distance measure. Okay, to quantify the change in time signal, one measure is to find the distance measure, and here we have used kb log distance measure to find the distance between the or the change between the two time signals. Okay, then we'll maximize that using some algorithm to find the optimal location. Before applying the kb log distance measure, we applied dynamic time warping to remove the delay between time signal, because here in our lab we use impact hammer to excite the structure, and you cannot control the time of hitting the time of applying the force. So there will always be a delay between the two time signals. So to remove the delay between the two time signal, so we use dynamic time warping. So it will just merge. It will just merge two signals so that it will remove the delay between the two time signals. So there will be no delay. So now we can apply the kb log distance measure between the time signal. So the kb log distance measure, it finds the distance between the signal 1 and signal 2. So it actually measures the distance between signal 2, the change signal, and the bound of the upper bound or lower bound of the signal 1. So it actually captures the area in these portions. So for the upper part, if signal 2 is higher than the upper bound of signal 1, so that portion is considered. And for the lower part, if the signal 2 is lower than the lower bound of the signal 1, only that portion is considered for the distance. So we'll add all these areas to find the total distance. So we used modified metrology hashing algorithm to find or to generate samples from the target distribution, where the distribution was, the target density was the of the random variables. So the random variables were the locations. So here x is the random vector, it represents the location of the sensor. So they are uniformly distributed between 1 and the number of nodes present in the structure. So if you have a FE model, if you have 50 nodes, so the location can vary from 1 to 50. So the sensor can be located at any position between 1 to 50. So they are random integers, non-repeatable random integers. So we generated non-repeatable random integer as x. So those are the unknown random variables, and we use the cumulative k-log distance as the acceptance criteria of the Markov chain. So using this algorithm, we found the optimal location of the sensor. So for the case study, we took the steel frame. So it was like the length was around 2.45 meter, height was 1.5 meter, and we had 4 bolts here, 4 bolts here. They are numbered like 1, 2, 3, 4, 5, 6, 7, 8. So for sensor we use accelerometers, and for time signal accelerations. So here we did the thing is we had only 6 accelerometers, so the number of accelerometer part we removed. So we said okay, we have 6, use the 6, using the 6 find the optimal location of those 6 accelerometer. If you have more than 6, you can use the same algorithm to identify the location of those sensor. So this is the FE model. We used Opensees to model the finite element, to do the finite element modeling of the steel frame. So we have 50 nodes, 40 nodes each along the column, and 20 nodes in the center of the beam. And to model the bolts, we used zero length link elements in the Opensees with varying stiffness and damping. So here mainly we varied the stiffness to represent the loosening of the bolts. So now when there is only one bolt loosened, we run the FA simulation without damage and with damage to find the optimal location. So these are the optimal location, the nodes here 6, 18, 22, 27, 28 and 30. So these are the optimal location of the sensor when you want to identify damage case 1. Similarly, if you want to identify damage case, maybe this is 5 or something, when 3 of the bolts loosen, these are the sensor location. For 4, these are sensor location, and when another case, these are sensor locations. So now the tricky part is, if you change the damage case, the sensor location they change. It's not the same. But in actual scenario, you don't know the location of the damage case. It means you don't know which bolt is loosened. That means you don't know anything about the damage. So if you don't know about the damage, then which case you need to consider. So the next step is, we said okay, there is no prior location of damage. We don't know the location of the damage. In this case, we consider the KB, the cumulative distance we measured, we simulated, and the Markov chain is moved forward when like we have 10 damage cases. Okay, so if the change in distance in all the 10 damage cases is larger than the previous time step. But if you use that, then you will get so many of rejections. So your Markov chain will not move forward. It will stop at some point. So to avoid that large number of rejection, we used a binary distribution. We said okay, not all the 10 damage cases it needs to satisfy. It needs to satisfy few of the damage cases. How many damage cases? That we can identify for a given probability. You will use the discrete binary distribution to find the number of damage cases it needs to satisfy. Okay, so based on that, we found the optimal location when there is no knowledge about the location of the bolts. Okay, so we found the optimal location of the sensor. Next, we need to compare that. So compare that with respect to the existing algorithm. So this location of the sensor is with respect to the damage measurability condition. So then, given by this paper, so then we estimated the global response sensitivity of the responses, the time signal with respect to the damage cases for our damage case and for our algorithm and for the algorithm given by this paper. And we saw that the total effect is higher, means it is more sensitive to the damage case. So if the total effect is higher, so in our case, we see the total effect for all the damage cases, we could see the total effect in our algorithm is higher than the existing algorithm. So we could say that okay, this algorithm is performing better than the existing algorithm to identify the end connections. So next conclusion and future study. Conclusion is okay, we could estimate the optimal location of the sensor, and we compared the efficiency of the algorithm with respect to existing algorithm is quite good. So based on the result, it's clear that acceleration time signals at the proper locations are more sensitive to damage than the existing method. So next iteration for the study, we did not stop there. What we are working on is like what is the minimum damage that can be identified. If you have a given number of sensor, say we have a 6 number sensor, like what is the minimum damage that we can identify? Yeah. So the next is, if we want to identify loosening of a single bolt, how many number of sensors we need? So that's another question we need to answer. And next is, could you combine different sensing method like strain gauge, accelerometer, a few other techniques, and could you improve the damage detection technique, the accuracy? So that's what for the study. So I want to thank my sponsors. Thank you for the